Hello and welcome to the presentation of F-PKI, enabling innovation and trust flexibility in the HTTPS public key infrastructure. I'm Cyril and this work was done in collaboration with my colleagues Laura and Adrian from ETH Zurich and Pratik from Princeton. The Web PKI is an integral part of the security ecosystem of the Internet. It provides a foundation of commonly used security protocols such as TLS, HTTPS, DOH and DOT. The security, stability and usability of the Web PKI is thus of utmost importance, which is shown by the plethora of improvements and extensions available. OCSP stapling, for example, fixes the problem of relying on an out-of-band communication to check the revocation status by providing this information via the TLS handshake itself. CT addresses the problem that misconfiguration and misbehavior of CAs was hard to detect. ACME allowed to extensively increase the coverage of Web PKI by automatically issuing certificates for a fraction of the cost. The Web PKI has one advantage, its simplicity. The only configuration required to set up Web PKI is a list of trusted root certificates. Every browser and every operating system comes with a set of pre-installed certificates, and everything works out of the box. However, we argue that this simplicity is also one of the major drawbacks of the Web PKI. On the left side, you can see that each participant of the Web PKI places equal trust into a set of CAs specified by a third party. Despite its numerous improvements and extensions, the core of the Web PKI is too rigid to work well in our heterogeneous society. A modern Internet PKI must allow for flexibility and individuality, as shown on the right side, where each user can have a different view of the world and thus trust different entities. Trust views are based on one's opinion and are thus potentially incompatible with each other. For example, the blue and orange trust views cannot be combined into a single unified view. The Web PKI has three main problems. The first problem is that at its core, a weakest link security model is used. Compromising any of the hundreds of trusted CAs allows the issuance of arbitrary certificates. The second problem is that there is no trust flexibility. If a trusted CA is removed, for example because a bogus certificate was detected, all certificates of this CA become invalid. This causes collateral damage since all domains using this CA no longer have a valid certificate and must request a new certificate from a different CA. In a sense, you have a trade-off between security and availability. CT reduces the impact of the weakest link security by allowing domain owners to check which certificates are issued for their domains via CT monitors. However, this provides no proactive security guarantees, since attacks are only detected after they have occurred and the bogus certificate is logged in a CT log. It also requires domain owners to perform self-monitoring by regularly fetching and comparing all issued certificates of their domain. Finally, CT monitors have been shown to have an inconsistent view, and thus a bogus certificate might not even be detected. All of these lead to a lack of innovation in the Web PKI ecosystem. The question that arises for a CA is, why should I be the first CA to implement a new security measure? There are no immediate security benefits for users, since all other equally trusted CAs are still vulnerable. As an example, Let's Encrypt started using multi-vantage point ACME validation from February 2020. But even if an attacker can no longer use hijacking to issue a bogus certificate from Let's Encrypt, the attacker can simply target any other CA using regular ACME. The second problem is that we cannot just remove CAs that do not implement security feature from the set of trusted CAs, since this would render a large number of secure domains unavailable. In this paper we propose F-PKI, the flexible PKI. In F-PKI there is no more weakest link security, since an attacker must compromise all trusted CA to attack a domain. There is a flexible notion of trust where users locally define their individual trust statements, and domain owners can define appropriate policies that suit their security needs. And as mentioned before, an unavailability of secure domains is not acceptable. F-PKI must thus initially coexist with the current Web PKI and be incrementally deployable. Also, updating web servers is often difficult in practice and might hinder deployment. For this reason, F-PKI does not require any changes to existing HTTPS servers. Finally, F-PKI makes use of the CT infrastructure and leverages existing certificate data available in CT. Here we show a typical HTTPS request in the Web PKI. The domain owner of example.com sets up a web server, generates a certificate signing request and sends it to a CA. The CA replies with the certificate and the domain owner installs it on the server. The client visits example.com and the browser establishes an HTTPS connection with the web server. The browser verifies the validity of the certificate and then shows a green browser bar to the user, indicating a secure connection. In the rest of the presentation, we show how F-PKI addresses the three problems in the Web PKI mentioned before, starting with the weakest link security. In the Web PKI, if any of the CAs is compromised by an attacker or misconfigured, such that the attacker can generate certificates for a victim domain, then the attacker can request a certificate and, for example, launch a man-in-the-middle attack. In F-PKI, instead of accepting any certificate signed by any trusted CA, certificates from all CAs are validated. This allows F-PKI to detect a certificate issued by a misbehaving CA and reject it. However, this immediately raises two questions. First, how can we fetch all existing certificates to ensure that an attacker did not hide any certificates? And second, if we have collected all certificates, how do we make the decision which one to accept and which one to reject? Should we, for example, reject certificates with different public keys? Or should we reject certificates issued by different CAs? Let's first tackle the second problem of how conflicting certificates are defined, and later on we will come back and discuss how a complete set of certificate is fetched in F-PKI. The next problem of Web PKI that we address is that domain owners have little control over which certificates are issued for their domain. We argue that conflicts must be defined by the domain owner itself. It is the only entity that knows which security policies are reasonable for the domain. In F-PKI, this is solved by letting the domain owner specify a policy which restricts which certificates are allowed to be issued for his domain. In this example, the owner of bank.com wants to ensure that a certificate issued for any of its subdomains will not be valid. The domain owner adds the desired policies to his certificate signing request, and they are then added to the certificate using X509 extensions. Among other things, policies can restrict which CA is allowed to issue certificates for this domain, which subdomains are allowed, if wildcard subdomains are allowed or not, and it can restrict the maximum lifetime of a certificate. Here you can see the regular Web PKI certificate validation. The relying party receives the X509 certificate from the web server during the HTTPS handshake, validates it, and either continues or aborts the HTTPS connection. In F-PKI, the relying party extends this validation process. The regular Web PKI validation is still performed identically, which means any certificate that is rejected by the Web PKI is also rejected by F-PKI. Additionally, the user locally defines its trust statements by specifying which CAs are highly trusted to issue the previously shown domain policies. In our example, CAs X, Y, and Z are such highly trusted CAs. The relying party queries our policy oracle, which we will describe in more details later, and fetches all policies signed by these CAs. Then, from all of the received policies, the relying party computes the strongest possible policy and uses it to validate the certificate received from the web server. Since all policies must be satisfied for a valid policy, the relying party combines the policies of all certificates to create the strongest possible, most restrictive policy. For allowed issuers and allowed subdomains, the values from different policies are combined using intersection. For binary values such as whether to allow wildcard certificates or not, the values are combined by a logical conjunction. And for duration values such as the maximum lifetime of a certificate, the values are combined by taking the minimum. Finally, after mitigating the problems of weakest link security and insufficient control for domain owners, F-PKI addresses the problem that Web PKI users cannot define individual trust statements. By using F-PKI as presented so far, there could be a single globally defined trust statement, which is CAs that enable multi-vantage point domain validation, for example Let's Encrypt, are highly trusted. If a domain owner then requested a policy from Let's Encrypt that, for example, disallows the issuance of certificates for subdomains, any user would reject a certificate issued for a subdomain. However, trust statements may not always be based on objective criteria such as multi-vantage point domain validation. Imagine two users, one from the United States and one from Switzerland, that both highly trust CAs located within their country. It is not possible to have a single trust statement as before, since both users highly trust a different set of CAs. In F-PKI, this is solved by allowing each user to locally define a function f, which defines which CAs the user considers highly trusted. Introducing this locally defined function f enables individual trust statements. However, what happens if the trust statement of a user depends on the validated domain? For example, the user highly trusts Google for google.com subdomains and highly trusts US CAs for .gov domains. How can the user describe such a trust statement using the function f? This is solved by making each trust statement depend on the validated domain itself. In the end, each user defines f as a function on the validated domain, which returns a set of highly trusted CAs for this domain. Earlier in the presentation, we defined our policy oracle, which returns all policies for a validated domain. In F-PKI, this oracle is implemented using map servers. Map servers fetch certificates from CT-log servers and provide a mapping from a domain to all existing certificates for this domain. Since policies are included in X509 certificates, a map server contains all policies for all domains. Note that these two requirements are equivalent to the requirements of a CT monitor. However, F-PKI uses a sparse Merkle hash tree to store all domain-to-certificate mappings, which allows an external auditor to verify its correct operation. Finally, the map server provides cryptographic proof for the existence or non-existence of a certificate to domain mapping. For more detail on map servers and how they are implemented, please take a look at our paper. Here you can see an overview of the complete system. All policies for a domain, including the cryptographic proof of a map server, must be delivered from the map server to the browser. There are different options for retrieving this data. In option A, the web server provides this data during the HTTPS handshake, similar to OCSP stapling. In option B, the browser fetches this data either directly from the map server or via DNS to improve privacy. Here we see the overhead of our proof of concept implementation. The implementation uses the Trillion framework for the sparse Merkle hash trees, core DNS for serving proofs via DNS, and a browser plugin to validate F-PKI proofs. For DNS, the latency overhead is negligible if the proof is fetched in parallel to the DNS request. But even in the worst case, if the DNS response is already locally cached and the map server must generate the proof on the fly, the overhead is still below 50 milliseconds in most cases. For the stapling approach, the latency overhead is typically below 100 milliseconds. Please note that a large portion of the overhead is due to our implementation of F-PKI as a browser plugin. We expect that in a native browser implementation, the overhead would be drastically reduced. To conclude, we designed F-PKI and provide a proof of concept implementation. F-PKI enables innovation and trust flexibility in the Web PKI by leveraging CT and an incremental deployment model. Thank you very much for your attention.